Chapter 19. The first section here has to do with oxidation-reduction reactions, and this is the section that I referred to earlier in the year when we were balancing equations. I said at that time that we didn't have all the tools necessary to be able to balance absolutely every equation. And in this chapter, we want to, in the few days that we have left, kind of learn about this process of balancing an equation. I'm thinking about putting one of these equations on your final as a bonus. So this would be the reason to learn this, but to be able to see that there are some other tools available. So in this first section here, we're going to assign oxidation numbers to reactants and product species. You've already done this back chapters back when we were learning how to write correct formulas. So this is kind of a review. And then we're going to find the terms oxidation and reduction. And then we're going to explain what an oxidation-reduction reaction is, or redox is what we often shorten it down to. So you can use the rules to assign oxidation numbers. These were the rules that we had, I think it was back in chapter 7. And oxidation-reduction reactions involve the transfer of electrons, and oxidation itself involves the loss of electrons. We're losing electrons, whereas reduction involves the gaining of electrons. So if you have an atom of an element that loses electrons, it's experiencing oxidation. If we have an atom of an element that's gaining electrons, it's experiencing reduction. Reduction are half reactions, and they have to occur simultaneously. One can't happen without the other. They don't have to happen exactly at the same spot, but they have to occur simultaneously. Now here is a table from chapter 19. Back in chapter 7, it wasn't so much as in this table form, but everything that's on here plus one extra one, I guess they've added here. I think number 2 is the addition from chapter 7. Otherwise, these are exactly the ones that you've had from before. And let's point out some things that are most useful. The number 1 is that the oxidation of any pure element is 0. A pure element means it's not combined with anything else. In other words, it's not in a formula. So an example that we have over here on the right is that we have sodium by itself. Pure sodium metal is 0 as our example. Then number 2 is we had you learn all these oxidation numbers or charges for all these different ions that are on your ion sheet. That is what number 2 is about. The oxidation numbers of the monatomic ions equals the charge of an ion. So for instance, you learned that chloride is a -1 as an example. So that would be an application of rule number 2. Rule number 3, it says the more electronegative element in a binary compound is assigned the number equal to the charge that would have if it were an ion. So remember, the electronegativity is on the back side of your periodic table, and the one that is more electronegative, and we learned that those are in the upper right-hand corner of the periodic table, are more electronegative, and those over on the left and toward the bottom are the most electropositive, or the least electronegative would be another way of saying that. So these have you will assign the one that's more electronegative the negative number. So if you don't know which one's positive, which one's negative, this is how you can decide. And now number 4, the oxidation number of fluorine in a compound is always -1. That's from before. We don't have fluoride as anything else than a -1. Oxygen is normally -2. We had only one exception that we had earlier, is that it could be -1 if it was combined, or if it was in a peroxide. And here they're adding a couple more things to it. If it's inside of like it says, unless combined with fluoride, in which it is going to be +1 or +2. In other words, if you have it with fluorine, which always has to be -1, then the oxygen might have to have some others. We don't have really many compounds that are like that. And then hydrogen, we learned, was always going to be a +1. The only exception is if it happens to be combined with a metal where it is less electronegative, then hydrogen will be -1 in that case. And then I think number 8 is probably worth pointing out. The oxidation numbers of all the atoms, remember, in a neutral atom is 0. So in other words, all the charges have to add up to 0, or oxidation numbers have to add up to 0. And if it happens to be a polyatomic ion, as it talks about in number 9, that particular one is, like as the example given over here, where you have H2PO4 and its overall is negative, then instead of adding up to 0, it has to add up to -1. So let's take what we've learned and apply it to a compound here like HNO3, hydrogen nitrate. What are the oxidation numbers of this element? Of this compound. Okay, so that is what we're going to try to do here. We're going to look at hydrogen, and it fits rule number 6, where it says the hydrogen's oxidation state in most compounds is a +1, unless it's combined with metal, and nitrogen is not a metal, so we know that hydrogen is going to be a +1. Okay, then we will look at oxygen next. Oxygen has because that's the next rule that we can use, has an oxidation of -2 unless it's combined with fluorine or is a peroxide, and neither of those exceptions apply here. So oxygen is going to have an oxidation number of -2. Now, just a reminder, this oxidation -2 is for each oxygen. So when you write a -2 up there, you're saying it applies to each oxygen, not all 3 oxygens together. Each oxygen's a -2. Okay, now all we have left to do is figure out nitrogen, and there's nothing on our chart that gives us that number, so we have to calculate this one. And we know this to be true. Hydrogen is a +1. Nitrogen we don't know in this part right here. We don't know nitrogens, but we know that oxygen's -2, and there are 3 of these -2s. So we know that oxygen's going to cause a -6. There's one hydrogen that's going to be +6, and for these to add up to 0, we know that this number right here, this is -6 + 1, is going to be -5. So this x has to be a +5 for it to add up to 0. So here's kind of the math of that. And so we now know that nitrogen has an oxidation number of +5. Okay, now if you add up those numbers right there, they clearly don't add up to 0. because we're talking about each atom's oxidation number, not the total charge. Okay, now oxidation occurs when valence electrons are lost. Valence electrons are lost. And processes in which the atoms or ions of an element experience an increase in oxidation state are oxidation processes. So let's use this example here where we have sodium, which would be burning in chlorine gas, and it forms NaCl, salt. Okay, and that's a balanced equation right there. In this equation, sodium, the first thing listed up there, is a pure element. It's not combined with anything, so from the rules that we have, it says that its oxidation number must be 0. But when we look at sodium at the right, it's combined with chlorine, and chlorine is -1 and sodium is +1. So we here have sodium going from 0 to +1, and in order to do that, this sodium, the first sodium, has to lose an electron. So this sodium that this electron that we have right here is a -1. A -1 added to a +1 would equal the 0 that we have over here. So sodium is experiencing oxidation. It has increased its oxidation state. Now by increasing, we think of, use the same number line that you do in math. Moving to the right is increasing, moving to the left is decreasing. And that species whose oxidation number has increased has been oxidized. So we could say sodium was oxidized. This is sodium's version of what iron does when it rusts, and we say it's been oxidized. Now, reduction occurs when the valence electrons are gained. So the processes in which the oxidation state of an element decreases this time are reduction processes. And in this same reaction that we talked about here, sodium burning in chlorine gas forming NaCl, table salt, the chlorine is going from 0. Why? Because the chlorine is a gas. It's not combined with anything, so the rule says that it must have a 0 oxidation number. And it over here on the right, we have chlorines in the sodium chloride, and chloride we know is -1. Each of these chloride ions is a -1. And we also have to make the number of atoms the same. So here's chlorine ends, remember it ends in INE, so it's a diatomic molecule. There's 2 of those. Each has an oxidation state of 0. And over here, each of them has an oxidation state of -1. So we're going from 0 to -1, but we're doing it twice. So for this to go, for each of these chlorine atoms to go to a chloride ion, it has to gain an electron, and there are 2 of those doing it. So we have to add 2 electrons to the chlorine molecule to become 2 chloride ions. And a species that undergoes a decrease in oxidation state is reduced. Decrease means moving toward in the negative direction. This one went from 0 to a -1. So we say that chlorine has been reduced. Now, oxidation reductions are paired reactions, we said earlier, and any chemical process in which the elements undergo changes in oxidation number is an oxidation-reduction reaction. And this name is often, as we said right at the very beginning, is often shortened to redox, so it's a little easier to say. And the part of the reaction involving oxidation or reduction alone can be written as a half reaction. So we remember they have to occur simultaneously, but we can write them in two separate pieces. So equations for the reaction between nitric acid and copper illustrate this relationship between half reactions and the overall redox reaction. So here is the part of that reaction where copper, because it says it is pure copper up there, going from 0, and in this reaction it's becoming a plus 2. It's going to be copper 2 ion, and so we put a plus 2 over it. So it's going from 0 to plus 2. That, remember, to go to the in a positive direction or increasing, we could say here, is the oxidation of copper. So copper is being oxidized. Now here is the nitric acid part, and here we see nitric acid has been ionized. It has to get this balanced, we have 4 hydrogen ions and 2 nitrate ions. Nitric acid is HNO3, and and we'll explain a little bit later why we have the water right here. But the important part to notice is that nitrogen over here in nitrate, remember it has to add up to a -1, is going from a +5 to, here is nitrogen dioxide. It's a molecule, and it's going to +4. So you notice it went from +5 to +4, and so it has decreased. It's going toward the negative direction, so it has been reduced. This is a reduction reaction. So if we combined those all together, this redox reaction would kind of look like this. We'd have copper with a 0 oxidation number. We have the nitrate ions where the nitrogen has a +5. Copper has gone to +2 on the right side, the product side, and nitrogen has gone to a +4 on the product side. So notice that the electrons that were lost by copper were needed for nitrogen to go from +5 to +4. It has to gain some electrons. Remember, electrons are negatively charged. And electrons are gained in the reduction, and they appear as reactants in the reduction half reaction. So here it was the electrons were a product. They were produced, but they were needed in the other half to complete the oxidation-reduction reaction. Now, if none of the atoms in a reaction change oxidation state, the reaction is not a redox reaction. And most of the reactions that you balanced earlier in the year were that type, where the oxidation state didn't change. So if you assign oxidation states to all the ions, ions in the reaction, and you notice that none of them change, that is not a redox reaction. Now, here is an example. We're going to take sulfur dioxide, and when it dissolves in water and it forms a sulfurous acid, which is H2SO3, not sulfuric, but H2SO3, sulfurous. Okay, and if we write all the oxidation numbers down there, okay, we know that oxygen's -2 almost always, unless it's with fluorine. And we have 2 at a -2, that's -4, so sulfur has to be a +4. And then in water, you know, oxygen's always -2, hydrogen's usually +1, so that would work out fine. We have +1 times 2 is +2, and -2, that adds up to 0 again. Now over here, we have to do a little extra work. We know each oxygen is going to be a -2. There are 3 of these, so that's -6. Each hydrogen is a +1, and there are 2 of them, so that's +2. So +2 plus what is a -6? Well, we need to have a +4. Well, so now each element has been assigned its oxidation number, and you'll notice that sulfur was +4. Over here it's +4. Oxygen's -2 everywhere it's listed. Hydrogen's +1, +1. So this has no change in oxidation state, so this would not be an oxidation-reduction reaction. Now, when hydrogen burns in chlorine, a covalent bond forms from the sharing of 2 electrons. We've learned that earlier. And the pair of electrons is more strongly attracted to the chlorine because it has a higher electronegativity. And so this will be the chemical reaction. It's a balanced one. We have hydrogen molecule burning or reacting with chlorine molecule, forming hydrogen chloride. And we have assigned the oxidation numbers on the top. Hydrogen is by itself, so it's going to be 0 in the first example here. Chlorine is by itself, it's going to be 0. But over here, they are combined, and so hydrogen takes on its +1, like from your ion sheet, and chloride is -1. So they have clearly changed. So that is an example of a oxidation-reduction reaction. So if we apply rule number 3, chlorine in HCl is assigned an oxidation number of -1. You got that from your ion sheet as well. And so the oxidation number of chlorine has changed from 0, its oxidation number in an elemental state, in other words, when it's by itself, to a -1 in the hydrogen chloride. So it's changed. It's gone from 0 to -1. So it has been reduced. And by rule 1, the oxidation number of hydrogen is 0. In the very first one over here on the right, this one's the 0, according to rule 1, because hydrogen's by itself. And according to rule 6, hydrogen, when it's combined with something else, will be +1 unless it was with a metal, and it's not with a metal. So hydrogen's gone from 0 to +1. It's increased its oxidation number, so it has been oxidized. It has been oxidized.